Right then, I promise you I'd try and show you where that formula came from for sin x. Let me just write it down again so you can see it. Sin x is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and that pattern continues on forever. An alternative way of writing that is to say that is the sum from r equals 1 to infinity of minus 1 to the power of r plus 1 x to the power of 2r minus 1 all divided by 2r minus 1 factorial. I think that's right. I'm sure you'll tell me if it's not, but I think that's correct. Okay, so I said to you, how on earth can we prove, kind of, that that is equal to that? Well, to do that, we're going to use Maclaurin's series formula. But we're going to do more than that. We're actually going to kind of derive Maclaurin's series formula for the general case. So I'm not talking about sin x now, just talking about f of x. So let's suppose for some function f of x, it's possible, and this could be sin x, could be cos x, could be e to the x, could be anything. It's possible to write it like that. So in general, I'd be saying it's possible to write it as an infinite polynomial, which I am now writing out. So my infinite polynomial, I'm just going to go up to x to the power of 4, contains powers of x going up from a constant with a coefficient in front of them, a number in front of each of the terms. And that would be f of x if it was possible to write a function as an infinite polynomial. Now what we're going to do now is we are going to find out a way of expressing the values of a0, a1, a2, a3 and a4 in terms of the original function. Because if I can do that, I can use the original function, this version of it, to actually discover the values of a0, a1, a2, a3 and a4. I should say at this point, there are some assumptions that are being made here, but I don't want to cloud the clarity of the video by going into this. So I'm going to ignore all of that for now and just show you how this works. So, nothing up my sleeve, I've done nothing wrong so far. I've just, apart from making a bit of an assumption that you can even do this, that if you've got a function, it can be written as a infinite polynomial. So what we're going to do now is we're going to differentiate the polynomial, this version of f of x, to find f dash of x. So that's just standard differentiation. So that term would disappear. That would become a1, and then I would get 2a2x, hopefully you can see what I'm doing, 3a3x squared, and then I'd get 4a4x cubed, and then there'd be some more terms off the end there like that. So that would be f dash of x. Let's do that again to get f double dash of x. So that disappears, and then I just get 2a2 plus, now I'm going to write this as not 6, I'm going to write it as 2 times 3, a3x, and then I'm going to write this as 3 times 4, a4x squared, and that was f double dash of x. Let's do f triple dash of x then. So f triple dash of x would be 2 times 3 a3 plus 2 times 3 times 4 a4 plus some more terms. Okay. Right. So I said that the reason we're doing this is to try and find a way of expressing A0, A1, A2 and A3 in terms of just f. And it turns out that we can do that if we set x equal to 0. So what I'm going to do is I'm going to sub x equal to 0 into each of these 4 expressions, left and right hand side, to come up with 4 new expressions, which are a lot simpler to look at and will allow us to do something rather miraculous. So if I put 0 in there, the other side just becomes A0, because all these terms disappear. I put 0 in for x. For similar reasons, the next one, f dash of 0, will just be A1. These terms would disappear. F double dash of 0 would be 2 lots of A2, and F, I'm going off the bottom of the page, sorry. F triple dash of 0 would be 2 times 3, A3. The reason I'm doing this is I'm trying to find a way of expressing A0, A1, A2, A3, A4 as well, etc., etc., in terms of F. And all I need to do to that is to rearrange these. So if I rearrange the first one, I get that A0 is equal to f of 0. A1 is equal to f dash of 0. And then I get that A2 is equal to f double dash of 0 divided by 2. And A3 is equal to f triple dash of 0 divided by 2 times 3. Okay, fed up on my iPad now, it keeps butting in every time I speak. So there we are, A0, A1, A2, A3. Now the pattern would continue. A4 would be F 4 dashes. I always wonder whether you should be putting IV or 4. Anyway, we'll talk about that later. Over, now it would be 2 times 3 times 4, but that's actually 4 factorial. And in general, a to the r is going to be FR of 0 divided by r factorial, like that. So, why do I want to know these? Well, because I can now replace, in this original version of f of x, all of the a terms here with terms that are based on f of x itself, which leads to the following formula, which is called Maclaurin's series formula. So if I put it there like that, you can see there's the original one. So what I'm doing now is I'm subbing in all those results. You can't see now, but you saw them a minute ago in the video. A0 was f of 0, so I'm going to write that as f of 0. A1 was f dash of 0. A2 was f double dash of 0 divided by 2, but I'm just going to write 2 factorial, which is actually 2. It's 2 times 1. And then the next one was f triple dash 0 x cubed over 3 factorial. And I've run out of space here, so I won't bother with x4. I'll just say that in general, you get a term which would be f r of 0 x to the r over r factorial. And this would kind of keep going on forever and ever and ever. This here is called Maclaurin's series. Sometimes it's called Maclaurin's expansion. And it's a way of writing a function as a polynomial as long as you can differentiate the original function and then work out some values for it. And we did it earlier with sin x. I'm going to show you it now with sin x. So if I start by saying f of x equals sin x, like so, and all I need to do to use this formula is I'm going to need to derive f of 0, f dash of 0, f double dash of 0, f triple dash of 0, etc., etc., etc. Okay? Well, let's start with f of 0 because I can do that really easily. F of 0 would be sine of 0, which is 0. Hence the first term is going to be 0. There isn't going to be a constant term. Remember, there wasn't. So let's try and get f dash of 0. Now to do that, I'm going to have to find f dash of x first. In other words, I have to differentiate sine x. Well, the derivative of sine x is cos x. I think you know that. So f dash of 0 would be cos of 0, which is 1. Etc, etc, etc. So f double dash of x is the derivative of cos x, which is minus sine x. So f double dash of 0 is going to be minus sine of 0, which is 0. There's no x squared term then. Oh, look, no, there isn't. It's all working. So f triple dash of x would be minus cos x, which, when you put the naught in, gives you minus cos of 0, which is minus 1. Now, if I keep going, I'll do one more. f4 of x. Oh, I did IV that time, look. Nothing like a bit of consistency. Well, the derivative of minus cos is sine. So f of 4x is equal to sine of 0, which is 0. Oh, we're going around in a loop here, look. It's going to go 0, 1, 0, minus 1, 0, 1, 0, minus 1. In other words, if I sub these values back into here, I get that sine x is equal to f of 0, 0, plus f dash 0 of x, which is just x. And then there's no term for the x squared. And then the x cubed is going to be minus 1 x cubed over 3 factorial, or minus x cubed over 3 factorial. That wouldn't be the next term, but the next term after that would exist, and it would be x5 over 5 factorial. And then I'd get the x, etc, 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 and we're done. So there you are. That is how you go from sine x to that. And the beauty of this Maclaurin series, don't just work for sine x, it works for, in theory, any function at all. You wonder how your calculator works out sine x? It just has a program in it that plugs it through this formula, and that's how it's getting its values. Clever stuff. Anyway, I will probably have attached some extra things to the lesson for you to try on this to get you going, but we'll talk more about it next time. Hope you found that fascinating and interesting. I certainly think this is a very exciting topic to introduce you to. See you soon.